We are going to talk about insulators and conductors in this lesson. But before then, let's recap what we've learned so far. We've come to realize that there are two kinds of charges in nature. They are positive and the negative charges. And there is this fundamental property that we need to keep in mind, that unlike charges attract one another and like charges repel one another. We've also come to realize that charges are conserved. They are neither destroyed nor created. So we can't create charges, we can't destroy charges. The number of charges in the universe are conserved. They remain the same. We also came to realize that charges are quantized. So the amount of charges that we have in any material, they come in steps of one basic charge unit. Today we are going to talk about conductors and insulators. And let's go straight. You should be familiar with these terms already. I only have to emphasize that the conductors and insulators we are going to discuss are with respect to electrical properties. Remember again that we have conductors for heat energy transfer. That's not what we are talking about. We are talking about electrical conductors. And the definition here is that electrical conductors are materials in which electrical charges move freely. Electrical charges are materials in which electric charges move freely, whereas electrical insulators are materials in which electrical charges cannot move freely. So keep this point in mind. Now we need to explain why conductors allow charges to move freely through them and why insulators do not allow electrical charges to move freely through them. The basic understanding goes back to the structure of atoms in materials. So let me show you this. Material will look like, we have the atom and the nucleus inside it. So we are only using this one to represent the atom. In fact, there are electrons that are in the shells. We are not interested about those electrons, but remember there are electrons there. Aside those bound electrons within the atom, there are other electrons that are not so strongly bonded to the atom. So those electrons become so free to move. They are not strongly attached to the atom, so they become free. This one will donate some of the electrons. This one atom will also donate some of the electrons, and these electrons are free. So free electrons from each atom are so many that they become like a sea of free delocalized electrons. The electrons are delocalized because they should actually be on the shell of the atom, but they are not there. They are somewhere. So they are delocalized. And they are free because they can move about. You see, they are not strongly attached to any particular atom, or yes, any particular atom. So they are free to move about. So this is what we call the free delocalized electrons. So this is an example of a conductor. So when we attach or we bring an electrical charge close to it, then you see the electrons either moving away or coming close to the source of the electrical charge. Alright, let me mention at this point that as it is now, there are equal number of protons and electrons here. You are seeing this one as an atom and there is only one plus there. Don't think that it is only one proton inside. This is a gold foil. So if you know the electronic configuration, so we have this atom here and there is only one plus inside, and you might think there is only one proton inside. Please be careful you are not deceived. There are so many protons there making up a whole charge. So we are only making things simple. That's why we have only one plus there. But there are so many protons there and so many electrons around this one, together with the ones forming the sea of electrons. So the number of protons in all the atoms are equal to the number of electrons here and the electrons forming the sea of electrons. So together, if you put everything together, this material is neutral. There is no net charge. The number of electrons are equal to the number of protons. So the material that you are seeing here is neutral. The charge is neutral. They are neutralizing each other. Now, if we should bring a source close to the material, then the electrons will rather be either shifting closer to the source or going away from the source. So this is the reason why conductors are able to allow electrons to move freely through them. So it is due to the free delocalized electrons in the conductors. Insulators do not have these free electrons in them. All the electrons are tied to one atom or the other. So they don't have free electrons, as you can see here. So that's the main difference between conductors and insulators. Because of that, for insulators, if you bring a source, another charged particle here, it will be difficult for the electrons to be attracted to that source or be repelled away from that source, depending on the charge of that source. We will see that shortly. Now let's look at how we can charge a conductor by induction. How we can charge a conductor by induction. Let's take this piece of conductor here. You should realize that we have the atoms that are designated positive charges. So the protons are inside there. And then the sea of the localized electrons, they are here. These electrons are free to move. So initially, before any charge can be applied to them, there are equal number of protons and electrons. So you can count them 1, 2, 3, 4, 5, 6, 7, 8. Then the electrons 1, 2, 3, 4, 5, 6. So there are 8 electrons, 8 protons. See, the protons are evenly spaced and they remain the same. The protons are not free to move. You should know that the atoms are not free to move about, but the electrons are free to move about. Now, in the second step, we introduce a charged object. So this rod has negative charges on them. If we bring it closer, we can now apply the first property of charges that we do know. So this one has negative charges, and you see that it is repelling the electrons away from the charged objects. Realize again that the atoms are not moving. The atoms that contain the positive protons are not moving. But then as we introduce this one, the electrons are moving away because like charges do repel one another. Okay. Now the next thing we have to do to this conductor is to earth it. When we earth it, the earth is a large reservoir of charges. What it means is that it can absorb excess charges, or it can release some charges to neutralize excess charges elsewhere. So since there are excess electrons here, the electrons will force themselves through this connection towards the earth, and they will move towards the earth to avoid the force that this one is exerting on them. Alright, so the next step will be that we need to disconnect the earth. If we disconnect the earth, there are now about 4 electrons left that are going to mix up with 8 positive charges here. So finally, if we remove the charged object here from there, we are going to have a net charge. That is, there will be 8 positive charges against 4 negative charges, and we are going to have a net charge of 4 positive charges. So this is how we can charge a conductor. Remember, this one is a conductor. That's why it has free electrons on them. We can charge insulators using this principle. Why? Think about this, write your own response and share with me. All right. So we will have to read about how to charge insulators, and that is straightforward. We can do so by induction. You can read about that one, or we can do that so by friction. That's you rub a cloth or something on the object, and some of the charges will be transferred from one to the other, leaving one object having excess of one type of charge and the other one having excess of another type of charge. You can read about charging by induction in insulators. Here is an example. You read about this one. In fact, you are watching Principles of Physics by Selway and Jewett. This page, Principles of Physics by Selway and Jewett. You can read about that pages. Let me check the pages for you. Pages 606 through 608. So you can read about insulators and conductors and how they are charged. Thank you very much.